All right, thank you for joining me today. I'm Chip Kent, the Chief Data Scientist at Deephaven Data Labs, and we're going to talk about real-time data science made easy. So to start, I'll give you a little background on my history and things that shaped my thinking. Way back in the day, I did scientific computing work, and then went on to do high-performance computing environments, and then spent quite a while as doing quantitative finance on Wall Street, looking at trading signals, things of milliseconds up to, in the long end, a couple of days, all real-time things. And then we took technology developed there and spun that out as Deephaven Data Labs, where I'm the Chief Data Scientist. So, real-time data science made easy. Let's talk a little bit about the scope of this talk. So, first of all, we're going to talk about real-time, we're going to talk about data science, we're going to talk about production quality, so things that actually work. Then we're going to talk about things that are easy for data scientists to use. There's a quick path to production. They're flexible systems using leading open technologies. And there are cases that work with structured and semi-structured data, since those are the most common use cases. We're not going to talk about software technologies that are difficult for data scientists to use. We're not going to talk about the many technologies out there without traction. We're not going to talk about legacy tech, and we're not going to talk about tech that requires major computer science investment. We want things that are easy to set up, easy to use. And we don't want to look at technologies that require a lot of labor to get going. So with that, let's look at what we're going to talk about. So first we're going to discuss why real-time, then what is data science and engineering, then real-time versus static, then smart real-time query engines. What are those? And next, using static libraries for real-time, finally building real-time data science systems, and then design patterns to use when constructing your own system. So first, why real-time? So by 2025, analysts estimate that 30% of generated data will be real-time data. This is 52 zettabytes of real-time data per year, and is roughly the amount of total data produced in 2020. This is an enormous amount of data. So soon, almost every data scientist and data engineer will be working with real-time data in one form or another. This could be data from finance, it could be e-commerce, could be Internet of Things, could be medical, could be computer security, or industrial, even transportation, metaverse. The future of data science is real time. So what do data scientists and data engineers do? It's an important question to ask as we look at real time. So as a group, we do data loading, data transformation, data cleaning, data pipelines, data curation, data exploration, data analysis, predictive model development, visualization, report generation, and we create proofs of concept. And as we move into real time, we need to do each and every one of these things in real time. So what is real time versus static? So if we look at, in this case, a table of data, to go from the table in the static world to a real-time table, the data can change. Simple concept. And these changes can be repeated over and over and over as new data comes in. So if we go just from real-time data to real-time data science, what does that mean? So we have a table. We may want to perform some sort of computation on it, and then as we get more data coming in, we can perform another calculation on it. Treating the data this way can be very inefficient if you're recomputing everything, and so that brings us to smart query engines for real time. So in real time, we have this changing data, and if you have a smart query engine, instead of looking at entire snapshots of data, you can look at changes in data and then incrementally update calculations based on these changes. So if we look at this table here, we have row additions. We also have cell modifications, and we can have row deletions, and you can have reindexing. And reindexing may be a little unfamiliar, but the concept is the data didn't change, but the order of the data in the table may have changed. So let's look at a case to kind of reinforce why computing on changes is important. So let's say you have a table like this one on the left that may be 1 billion rows long, and we add one new row. Really, you don't want to recompute the entire table just because one new row is added. Why not just recompute the row? And you can come up with many, many, many examples like this, but it is universally true that computing on the changes ends up being much more efficient than recomputing on the entire table. So, can't I just use my favorite static library? Whether it's NumPy or Pandas or TensorFlow, PyTorch, whatever. Can't I just use that on real-time data? And the answer is, well, maybe. So there are a few cases where it would make sense. So first case, your data is really small. In this case, if your data is small enough and you can recompute everything every time the data changes, and that ends up being okay. There are problems like this. But if your data ticks quickly or changes often or is very large, this just doesn't work. Second case, we can take snapshots of the data. So occasionally a snapshot of the real-time world is grabbed, and then computations happen on that snapshot. This gets around problems of keeping up with data changes, but with very frequent data changes, but at the same time, it's somewhat compromised because you don't see everything that is changing in the data, and that could potentially be a problem. The third way you can use your static libraries is integrating with a smart query engine. In this case, the smart query engine is taking care of these table changes, and you can integrate into the query engine so that when these calculations on changes happen, it's using your static library. So now let's look at building real-time data science systems. So open real-time data software is like Legos. You can think about each Lego performing a specific job, and to create a real-time data science system, you need to grab Legos that perform different jobs and stick them together. For example, you may have a ksqlDB query engine and a Deephaven query engine hooked to a redpanda data backbone with with gRPC for communication. So when you're building a system, you have two key questions. First of all, what does my system need to do? And second of all, to accomplish that, which Legos do I need? So the Legos for building real-time data science systems look like this. First, you need a way to get data in. You need a way to get data out. You need a layer for communication. You in many cases, want to persist histories so that they can be used later. You need a query engine to do some computing, and frequently you have clients, and these clients can be user interfaces, they can be plotting, they can be visualization, they can be dashboards, they can be other systems. So the first layer to talk about is where real-time data moves and lives. So in this layer, there are two key pieces. The first piece is your communication layer, and the communication layer lets different parts of your real-time system talk to each other. The second key piece in this layer is the persistent storage, which allows you to store data for use in other components. So in this world, Kafka is a key component. So in the old static world, you tended to have systems built around SQL databases, and the SQL databases would get updates when new data came in, or they would get deletions when data was removed. But Kafka serves a similar purpose in the real-time world. So in this case, everything in the real-time world, everything gets recorded as Kafka events. And so Kafka is going to provide both your communication and your storage. Then a recent alternative to Kafka is redpanda. And so redpanda is a re-implementation of Kafka in C++. And what that means is anytime you use Kafka, you could use redpanda because their interfaces are the same, but you can expect redpanda is typically going to be faster. One other set of changes redpanda has made are designed to make administering the software easier. So in general, you should find redpanda easier to administer than something like Kafka. Another communication technology that you may be less familiar with is Barrage. So if you look at Kafka or redpanda, those are both designed around the concept of streaming. So you just keep getting new data as streams. Barrage is kind of a different concept. Barrage is meant to communicate tables of data and including the changes. And so, if you look at what we discussed earlier, these changes can be adds, modifies, deletes, and reindexes. And so Barrage takes Aeroflight, which is a common memory format for tables of data, and extends it to real time and allows those real-time tables to be communicated. Because Aero is a memory format for real-time tables, it is portable between different programming languages, and so that helps you as you build tools on top of it. Now let's look at query engines. And query engines are where data science happens. So first of all, what is a query engine? So first, query engine takes data in, and then it performs operations on it. These operations could be filters, they can be joining, they can be aggregating, transforming, it can be math, AI, computation. And then after performing these really data science calculations, the query engine has a way to output the data. So you can think about the query engine as being the brains in your data science pipeline, and the brain is what's doing the data science. So a key question with the query engine is, what is the query language? And these query languages tend to break down into two primary categories. The first category is SQL. So SQL is a common programming language. Many people are familiar with it. It's been around for years. It is good if your use cases are fairly simple, but as your use cases and your data science get more complex, it can be problematic. SQL's integration with Python tends to be quite shallow, and SQL generally has little or no time series support. The second category of query languages I'm going to call data frame languages. And these are things that are analogous to working with a data frame in pandas or in R. And so these are something new to learn. They're not something old like SQL. They tend to be very flexible. They have deep integrations with Python, and they support time series. So if you're looking for a SQL type language, something like ksqlDB or Materialize or Spark, or query engines that support this. If you're looking for a data frame type language, Deephaven and Spark would support that. So let's look a little more at what these query languages look like and the implications. So if you have a simple query like this one here, we take a page views table and we perform a filter on it where we filter timestamps within a range. On the top you can see a Deephaven query, which is a data frame type query, and it's very readable. On the bottom you can see the analogous SQL query. Again, it's very readable. And if you're doing these simple things, either SQL or data frame languages end up working out very well. If you go to complex queries, you see more differences. So in this query here, two real-time tables are, first of all, joined using a time series join. Then a new column is added, and that column is computed using a Python function. And then a subset of those columns are retained. The table is grouped based on a column. A new column is added and computed from a formula, and then that table is ungrouped. So you can see with this data frame type language that's fairly easy. Doing that in SQL is likely a nightmare, and it's not something I'd want to do. So as you're considering a query engine, think very carefully about the query language and the types of problems you're going to be solving. So the first query engine we'll talk about is ksqlDB. This is just SQL for Kafka, fairly straightforward. So as you'd expect, the query language is SQL. There's a command line where you can interactively work with data, but it doesn't provide visualization, and the time series queries are very limited, basically to things like windows of data. Another query engine is Materialize. This is SQL for Kafka with consistency guarantees. So again, your query language is SQL. There's an interactive command line. There's no visualization and no time series queries. Now we can move to something like Spark streaming. So Spark streaming is, as you might guess, Spark for streaming data, and it is an evolution of Spark. With Spark streaming, streams of data are broken up into smaller batches, and then these batches, you can use basically the Spark compute engine to operate on these batches of data. So this is good and bad. On the good side, you get the power of the Spark compute engine. On the bad side, this was basically a new requirement that was added late in the Spark development cycle, and you end up with typical problems where requirements are added late in a software project. It's not what you would design if you started from scratch with real-time streaming requirements. So if we look at the query languages for Spark streaming, it supports both SQL and data frames, which is great. You can pick the particular language based on your problem. There's an interactive command line for interacting with data. Visualization, I'm actually not sure what's available for the streaming side. Spark, on static data, there is visualization, but there is little to no documentation for creating visualization on streaming data with Spark. And Spark does have time series queries, which is fantastic. And the last query engine we'll talk about is Deephaven. So Deephaven Community Core was born in the quant finance world. You can perform very complex queries. It is very good at interacting with data. There's plotting and visualization to go with that, and it was designed for high performance. So Deephaven is the query engine that is that is operating in the background of many of the world's largest hedge funds, banks, and exchanges. The query language is data frame based. There's an interactive command line. You get an IDE for visualization while you're working with data, and you have the ability to do advanced time series queries. So just to kind of show you what a real-time interactive environment looks like, you can see here you have an interactive command line, you have your code you're working with, you can see your real-time tables as they're changing, you can also see real-time plots, and you can interact with these plots. And this ends up being a good thing for touching and feeling the data. So let's go on to design patterns. So a software design pattern is a general reusable solution to a commonly occurring problem within a given context in software design. And what that means for real-time data science, we're going to look at common ways of selecting Legos and assembling them so that you can create a real-time data science system that works without having to reinvent things. So the first pattern we'll look at is an as simple as possible case. So there's no data backbone and we have no persistence. So in this case, you have a way to get data in, you have a query engine, a way to get data out, and then you can have clients for plotting, visualization, dashboards, and things like that. And this example was done with Deephaven because it's one of the few query engines that can operate without infrastructure for a data backbone. So here I'm going to show you how simple it can be. Start just with a pip install of a Python library for Deephaven, and this will take a few seconds. Okay, now we have a script that will start Deephaven and perform a query. We will run this script from the command line, and now that the script is up, switch to a web browser with the real-time data science environment. In just a few seconds, you can be up and playing with real-time data science. And as simple as possible, that's very easy. Now let's go to the second pattern that's a little more complicated. In this case, we have a data backbone, we're going to have persistence, and we're going to have a query engine. So here, your communication backbone would be Kafka or redpanda, and we would hook a query engine to it. This query engine could be Deephaven, ksqlDB, Materialize, Spark. Any of these are fine. And the way this would work is the query engine would read data in from Kafka, perform its calculations, get its outputs, and then those outputs would be sent right back into Kafka. Simple idea. Now we can take that design pattern 2 and make it a little more complicated. In this case, we have the data backbone, we have persistence, but instead of having one query engine, we'll have multiple query engines. So each of these query engines, like before, talks to Kafka. It reads data from Kafka as inputs, does its calculations, it sends the outputs back to Kafka as new topics. So in this case, you can think of these query engines as being like microservices. Each one is dedicated to a particular real-time calculation. And there's no requirement that the query engines be the same. So for example, you could have a Deephaven query engine and a Materialize query engine, and potentially a third query engine, which is a Spark query engine, and they could all work with each other and talk to each other because they're going through the same Kafka backbone. Anyway, it's a very nice design pattern, and you can scale things up as you add new queries, and you can match the query engine to your particular problem. Okay, design pattern 4 is a client to the query engine. So in this case, you have a query engine that's up and running. It could be any of these cases we discussed, and then you have a client application that talks to the query engine. The client application could be Python, C++, Java, JavaScript, Go. It doesn't really matter. All that matters is that the query engine supports the client for the language you care about. So in this case, the client can subscribe to outputs from the query engine and then get the data and do things to it. A client could also potentially perform calculations and then send results back into the query engine. These clients could be other real-time systems, they could be user interfaces. Really, it is quite flexible. Okay, fifth pattern is Jupyter. Jupyter is a key tool in the data science world. It is a way for trying out new ideas. It is also a way to combine text with calculations to communicate ideas, and it is essential in the workflows of most data scientists. So in pattern 5, we are going to look at Jupyter in the simplest case. We're going to have no data backbone, no persistence, and we're going to embed the query engine directly into Jupyter. So that would look like this. So you have Jupyter, you have the query engine running inside Jupyter, and then you have your clients running inside Jupyter. And in this case, your clients are the GUI widgets that are going to display tables, plots, and other real-time data. So we can look at an example of that here. We have Jupyter. Did this example with Deephaven, but you could do this with other query engines. Sorry, you can't do this with other query engines because this is the simple embedded case. But you can see we've popped a real-time table up here in a manner that's very similar to how you might see just a static pandas table displayed. The next more complicated case is we have Jupyter, but we have a data backbone with persistence, and we have a query engine attached to the backbone. So that case would look like this. Here you have Jupyter. Inside Jupyter, you have a client, and that client talks to your query engine, which is communicating with your Kafka or redpanda backbone. And if you have a large team environment with Kafka set up, this is typically how you would do Jupyter. So in summary, let's go through the key concepts I hope you remember. So first of all, open real-time software is like Legos. Each Lego performs a particular task, and to build your real-time data science system, you figure out which Legos you need and you hook them together. Next, with real-time data, it is inefficient to totally recompute every time your data changes. You want to avoid that, and it is smarter to compute based on changes in your data, and these changes can be adds, modifies, deletes, and reindexes. Next, when you're picking a query engine, Think very carefully about the query language supported by the query engine, and make sure it matches your use case. So you have SQL type cases where you can use ksqlDB, Materialize, or Spark, and then you have more expressive data frame type languages supported by Deephaven and Spark. Finally, use established design patterns. There are a lot of work has gone into what are robust Legos to use and how to assemble them to accomplish what you want. There's no sense in reinventing this. Just get a design pattern that's been worked out and build from there. Finally, I'm happy to take any questions. You can contact me after this at chipkent@deephaven.io if there's something you'd like to ask me directly. Also, the Deephaven Community Slack link is right here. If you're getting into this field and you want to kind of talk about your particular real-time data science problem and how you might build out a system, this is a great community that can answer questions. A lot of experience there. Also, if you just want to give kind of this real-time world a try, if you go to deephaven.io, there's a button you can click to spin up some hardware and get a demo system. And in the demo environment, there's some real-time data and some examples you can try. And I believe Materialize has a similar environment if you're looking at more of a SQL type query language. And with that, I am happy to take any questions. Thank you.